Hello everyone, welcome to our differential equation class. In this video we introduce the eigenvalues and eigenvectors of a matrix. We start saying why this idea of eigenvalues and eigenvectors is useful to solve differential equations. Then we introduce the precise definition of eigenvalues and eigenvectors of a square matrix. Then we are going to talk a little bit about the geometrical meaning of this idea, and we end up this video computing analytically eigenvalues and eigenvectors of a simple matrix. So that's the plan for today. Let's start with a little bit of history, and the first mention of the concept of eigenvalues and eigenvectors of a matrix was done by Augustin Cauchy around the 1840s, when he tried to solve a system of differential equations of the form x prime of t equals some matrix acting on x of t. Here, this matrix is an n by n matrix. Let's suppose it's a constant matrix. And here we have our variable vector, which is an n vector valued function of t. This equation is a generalization of the scalar version of this equation, which we have studied in previous videos, which is y prime of t equals some constant times y of t. This is the well-known exponential growth equation. Here we have one single function of t, a is a constant, and the derivative of the function is proportional to the value of the function. This is the generalization of the exponential growth equation from scalar equation to systems. We know what the solution of the scalar equation is, the exponential growth equation, because these are exponentials. Y of t solutions are proportional to exponential at, where here the c is a constant, is a number. So this type of solutions of the exponential growth equation motivated Cauchy to guess that the system could have solutions of the form x of t equal, just like before, a constant, but in this case the constant should be a vector, and then exponential of some number, let's call it lambda t. So as before, here the constant is different from 0, so we are looking for solutions where the vector is different from 0, and this constant here is the Greek letter lambda. It's just a name. So these are the generalization of solutions for that equation. So we are going to try to see if this type of functions is actually a solution, or when this type of functions are solutions. So what we do is we put that into the equation. So what we're going to do is we're going to put that into the equation on this side and on this side, and we see what we get. So on the left side, we are going to have v, the vector v. Let's write it down a little bit better. A vector v exponential lambda t, and we have to compute the derivative of that. On the other side, we have the matrix A acting on that vector v multiplied by the exponential lambda t. So that is what we have when we put that into the equation. Now, the derivative on this side, well, it's easy to do because this vector is a constant. So the derivative is only gonna act on the function of t. Recall this prime here means, so let's write it somewhere. Prime means derivative with respect to t. So because of that, we are going to get the vector v. The derivative of the exponential is going to be lambda exponential lambda t. And on the other side, well, recall this is a vector, this is a matrix. Matrix act on vectors. This is a scalar that multiplies all the components of the vector are multiplied by exponential lambda t. But this is a common factor outside the vector, so we can keep it outside, and we can just compute the matrix acting on the vector, and to that result we multiply by the exponential. All that, what it means is we can write the exponential here, lambda t, and then a acting on the vector. But we have exponentials on both sides, so we can cancel them out. And then we end up with the following equation that lambda and v must satisfy. And that equation is that lambda times v has to be equal the matrix A acting on V. So the solution proposed, which is this solution here, this function here, is going to be a solution of this equation if and only if V and lambda satisfy this equation. So this we are going to see pretty soon. This is the equation that defines the eigenvectors and eigenvalues of a matrix A. So this is how you find the equations for eigenvalues and eigenvectors of a matrix when you try to solve a system, a first order system of differential equations. Cauchy did this calculation around 1840, but later David Hilbert arrived to a similar equation given a matrix, a similar equation for a vector and a number, while solving another type of equations called integral equations. And it was Hilbert that he named the number that appears here, lambda, as an eigenvert. Well, he was German, so this is eigenvert, and in German this means proper value. And v, the vector, he called it eigenvector, so proper vector. And we took the names from David Hilbert, and v is now an eigenvector, lambda is an eigenvalue of a matrix A. So this is a little bit of history where this concept came from, and now maybe it's a good idea to introduce the precise definition of an eigenvalue and eigenvector of a matrix. We are going to say that a number lambda and a non-zero vector, recall v has to be non-zero, a non-zero vector v, are the eigenvalue and the eigenvector of a square matrix A. Notice that the matrix has to be square if and only if this lambda and v satisfy this equation. The action of the matrix on the vector is proportional to that vector. So and now hopefully we understand why we are interested in this equation, because when lambda and v are solution of this equation, this function here is going to be solution of that differential equation. Okay, a few remarks before we start exploring this concept a little bit deeper. A few remarks. This equation, the eigenvalue eigenvector equation, that is a matrix acting on a vector equal or proportional to the same vector, where here in this equation the only thing that is given is the matrix A. A is given. This equation is a little bit harder to solve than an equation that looks the same but is not the same, the equation AX equal B. In this case, in this equation, A, the matrix, and the vector B are given. I mentioned this difference because this equation we know how to solve it. If matrix A, for example, is invertible, we multiply by the inverse, and then we have X. Solved is given by this formula. but because b is given, so we can compute x. But here, this equation is not the same as this equation because the right-hand side of the equation is not given. Here, b is given, but here is not. So if you multiply by the inverse, you're going to get that v inverse of matrix A is lambda A inverse V, and you are exactly in the same place you started. So you haven't solved anything. So this equation is a little bit harder to solve than this equation. Okay. Other comment, second comment, is that the eigenvalue, eigenvector equation, sometimes we call it eigenpair, the eigenpair equation does not determine the length of the vector v. So the length of the eigenvector is not determined by the equation. So what do we mean by that? In other words, suppose you have a vector v that is solution of the eigenvector equation. Then any multiple, any non-zero multiple of that vector is also a solution. To see that, let's write a little proof of that statement. Suppose we have a v is solution of the equation AV equal lambda v. Okay. So now let's multiply this equation, and suppose a is different from 0. Let's multiply the whole equation by a, in any number a non-zero. So we are going to have a here that multiplies a matrix A acting on the vector v, and here a lambda v. Now we use that notation that with parentheses, saying that this is a constant that can be anywhere, so we are going to put that constant inside the vector v. So to do that, we use parentheses. AV means the constant a is multiplying every component of the vector v, and so we do here. So we keep the lambda outside, and we put the vector v here with the constant a. But then this is the whole proof. It means that if v is a solution of the equation, the vector AV with the multiple is also solution of the equation 1. Let's call this equation 1. You see? V solution, so AV is. And that's it. So the equation does not determine the length of the vector, only the direction. Let's see an example of an eigenvalue and eigenvector of a matrix. So in here we need to verify that this matrix, 2 by 2 matrix, square matrix, has eigenpairs, so eigenvalue and eigenvector, these go together, and eigenvalue and eigenvector, these go together. So before we do that, let's start with a little remark that not any vector is an eigenvector. For example, let's grab that matrix, matrix 0, 1, negative 2, negative 3, and let's grab the vector 1, 0. This is the vector that is the horizontal vector. When we draw it on the plane, is the horizontal vector with length 1. Okay, actually this is called the vector I, sometimes by physicists. And this is our matrix A. Okay, what is that equal to? Well, we do the matrix vector product, so we have 1, 0, 0, 1, so this is 0. And then let's write it down in a different color. Yeah, let's write it down in a different color, in green, 0. And then this vector times that, so that column times this row, we are going to get a negative 2. Okay, so we put a negative 2. Well, this is a vector that actually is pointing in a different direction, in the vertical downwards direction, isn't it? It's 0 horizontal, negative 2 component vertical, So we can write it down also as -2 if we want the vector 0, 1. But so in other words, this is -2 times the vector j. This is how it's called, that vector by physicists. Okay, so this is what we get here. The matrix A acting on this vector give us a vector in a different direction. So if we draw what we computed, we have the vector I, which is going to be this vector here. Let's suppose this is I. This is the vector 0, 1. 1, 0, sorry. And then we got, as a result, the vector negative 0, negative 2. So this is the vector negative 2j. So you see the matrix, this is actually, the vector here is actually A acting on the vector I. So when we have this vector, the action of the matrix on that vector is to change that vector into this other vector. So we change the direction. So this is what matrices usually do. In general, matrices acting on vectors change the direction of the vector. Well, but this is an important remark because that cannot happen for an eigenvector. Recall what is the equation for an eigenvector. V is an eigenvector of matrix A if the action of the matrix on the vector is proportional to the same vector. So this vector and the original vector are V and AV are on the same line. So let's see that this is what is happening. Solution. Let's verify. Recall what we need to do in this problem is verify that this vector is an eigenvector of the matrix and this is the eigenvalue. Okay, so let's write down the vector. So the matrix acting on the vector is the matrix 0, 1, -2, -3, and we want to act on the vector. What vector is that? 1, -1. 1, -1. Okay. Recall what we are doing here is nothing more than A acting on the vector v1. The vector v1 here. Okay. So let's do the matrix vector product. What do we get? Well, we get in the first component we get -1 when we do that, and when we do this we get -2 plus 3, so +1. Well, this is not the same vector, but notice that we can pull common factor a -1 outside, -1, and then here we are going to get 1, -1, which is the same vector we started with. So what we get here is -1 times the vector v1. Okay, so what this says, this equation says then is that v1 is an eigenvector with eigenvalue 1. Lambda 1 equal, -1. Okay, so we can do a little picture. What is the vector we are working with? 1 horizontal, -1 vertical. Okay, let's do it in blue. It's 1 horizontal, -1 vertical. So that should be more or less this vector here. There. This is the vector v1. And what is the result of the matrix acting on the vector v1 is negative that vector. So the result, we are gonna do it in green, and it's gonna be more or less this is not in the right place. If that should be more or less over here and over there. Okay, so the vector a v1 is actually this vector here, more or less over there. This is the vector a acting on v1, and you see they are on the same line. The eigenvalue is negative, so it moves the vector 180 degrees to the other side, but they are on the same line. They are proportional to each other. Okay, let's verify that the other vector is also an eigenvector. We have the matrix A acting on the vector v2. The matrix A is 0, 1, negative 2, negative 3. What was the vector v2? Vector v2 is 1, negative 2. Okay, 1, negative 2. Okay, what do we get in the first component? We are going to get negative 2. What do we get in the second component? We are going to get negative 2 plus 6. Negative 2 plus 6 is 4. Okay. So again, not the vector, but if we pull common factor in negative 2 on the whole vector, we are going to get negative 2. And here we are going to get 1, negative 2. And we end up with negative 2 multiplied by v2. So what that says is that v2 is an eigenvector of matrix A with eigenvalue lambda 2 equal negative 2. So if we draw the vector, what vector is the vector 1, negative 2. So let's go in blue, is the vector 1, negative 2. So that vector here. Okay, so let's see if we can draw it more or less over here. That should be our vector v2, and then the matrix acting on that vector is negative 2 times that vector, so is the vector negative 2 horizontal, 1, 2, and then 4 vertical, 1, 2, 3, 4, right there. So let's draw it more or less up to there. This is A acting on v2, and again they are on the same line. So this is how an eigenvalue and an eigenvector of a matrix looks like. And these are particular vectors, particular directions, where the action of the matrix is on the same line as the original vector. Let's go a little bit deeper into the geometrical meaning of the concept of eigenvalues and eigenvectors of a matrix. And to do that, let's use the following example. Use a graphical representation of this function. The function is given by a matrix, to find its eigenpairs, that means its eigenvalues and eigenvectors. So now we have this matrix, the matrix 1, 3, 3, 1. And we want to use a graphical representation of the matrix as a function. So let's recall a little bit how we did the graphical representations of scalar functions, functions from numbers to numbers. Suppose we have a function f that goes from the real numbers into the real numbers. So y is a number associated to x by the function f. So this function changes numbers into numbers. And an example, any function you know, for example, f of x equals sine of x. A graphical representation of this function, what we do is Well, we do it on the plane, on R2. Oh. And we put, so this is the space R2, and actually is formed by the space R here, which is the values of the domain of the function, and then we put here another copy of R, but in this case for the values of the range of the function, so the result of the f acting on x. And then for each point on the plane we can graph, so for x here we can graph what is the corresponding y, and then we obtain this curve, for example, for the sine function. This is what we usually do, and what we need is two copies of the domain and the range. This is the domain space, this is the range space. We put them together and we can do the graph of the function. Suppose we want to do the same with this function here, the matrix function. Well, then something is not going to work, because this type of picture is not going to work, because the matrix is a function from the space of vectors with two components into the space of vectors with two components. That is, given a vector x with two components, matrix A is going to give you a new vector, changes vectors into vectors. But we cannot do a graphical representation like this, because our domain is R2 and our range is R2, so we need R4 to do the graphical representation equivalent to this one. But we don't have R2, we live in R3. So we can do a graphical representation of the domain. For example, here we can put any vector we like, the vector x. But if we want to graph what is the corresponding vector by the matrix, we cannot, because we have only one component of y and not two. So we don't have enough dimensions to copy this type of graphical representation from scalar functions into matrix functions. So we need to do something else, something not so pretty as this type of graphs. And one thing we can do is, well, we can keep the domain space and the range space separated. So we graph any vector on the domain in R2. This is domain space. So we usually pick up any vector here, and then the matrix is going to change it into some other vector also in R2, but is in the range space. Now we are in the range space. So for example, this vector is associated by a matrix A into that vector. And then any vector on this circle is associated, so grab any vector here on that circle, and it's going to be associated to a vector on that ellipse. So then we can see more or less what the action of the matrix is doing, because we have one circle and the matrix deforms that circle into an ellipse. That's the best we can do for 2x2 matrices to understand the geometrical meaning of the function given by the matrix A. Because another thing we can do is we can put the domain space and the range space in one copy of R2, because the domain and the range spaces are the same in this particular case. This is only for 2x2 matrices. So let's put it here. This is for matrices 2x2. As soon as the matrix is a little bit bigger, we cannot even do this type of representation. For example, for a matrix 4x4, we cannot do it anymore. But up to 3x3 or 2x3 or 3x2, we can do this type of representations. And in the case of square matrices 2x2, we can put domain and range space together like this, which is what we were doing here. This here, that's why we are using different colors, because blue is vectors on the domain, green are vectors on the range space of the matrix A. So we can do the same here, and we can say this is the vector on the domain and the action of the matrix. So let's put here matrix A. The action of the matrix changes that vector into that vector. And in an analogous way, analogous way, the circle is deformed into an ellipse. We can put both circle and ellipse in the same space, blue for the domain, green for the range. So that's what we can do, and we can do this type of pictures also for scalar functions. We never do because it's not as nice as this type of pictures, but we could, and we would end up in using two colors for domain and range, and these are points. This point is moved into that point by the action of the function f. But you see, it's very uncomfortable to do that because we can do much better for scalar functions, but we cannot do better for matrix functions. So we need to do this type of graphs to understand the geometrical meaning of a matrix as a function. Now that we know what we are going to do this type of pictures or this type of pictures. Now we can go back to our example, find the eigenvalues and eigenvectors of this matrix using this type of graphical representations. So what do we mean? So for example, what we want to do is solution. We want to try different vectors. For example, on the matrix A, on the matrix M, for example, M. So let's write matrix M 1 3 3 1. What we want to do is, okay, we want to see what is the action of this matrix on any vector. For example, on the vector 1 0, and here the result is obviously going to be a green vector, and the vector is going to be 1 3. And you see we change the directions. This is a vector that is horizontal, and we change the direction of the vector into a vector that is more or less like that. Actually, we can do it a little bit more precise. Here we have domain and range. Again, on one picture, the vector on the domain is the vector v, and this is the action of the matrix on that vector. It changed the direction, so this vector can never be an eigenvector of that matrix. So how do we find eigenvectors? We keep trying different vectors here, and a vector here, a vector there, a vector on any point on the circle, and we see what is the result, the action of the matrix on those vectors, and we identify from there which ones are eigenvectors and which ones are not. But we are going to use a computer program to do that. So let's jump into the computer now. Okay, here we have our computer program. Here we have our matrix M, which is 1 3 3 1. We can change the component of the matrix later on with these sliders, but let's keep it 1 3 3 1. This is our vector 1 0. The action of the matrix on that vector, this is the vector 1 0, is the vector 1 3, as we computed before. Any vector on this circle is going to be mapped into vectors on the ellipse, as we are going to see in a minute. Here we can change the length of the vector on the domain, and here we can change the angle. So we are going to use that this slider of the angle to move the vector along the circle and see if we can identify eigenvectors. For example, this is not an eigenvector because the action of the matrix on the vector v is a vector that is pointing in a different direction. Eigenvectors must point in this along the same line. So let's see if we can identify an eigenvector. So no eigenvector, no eigenvector. Up here we have one close to that. So you see this, the action of the matrix on this vector is on the same line. Actually, let's do is 44. I think I'm guessing that actually if we put 45 here, let's see if I yes, 45 there. Now is a perfect match. And what is the eigenvalue? So you see these are the components of the eigenvector. So what is the eigenvalue? So what about if we make a vector a little bit longer, because any multiple of an eigenvector is an eigenvector. Now this vector has component 1 and 1. Well, not quite, but almost. But you see what is happening. The components have to be the same. So for example 1 1, and then what is the action of the matrix on that vector is 1 2 3 4 4 4. So here we see that the eigenvalue is 4. Eigenvalue 4 for the vector, for the eigenvector, which is 1 1. Okay, let's keep moving. We have one eigenvector, and there we have another one. 136, I think is 135 actually. Let's see if it's true. Yeah, it's perfect now. So you see this, the vector negative 1, so the vector negative 1 1, and the result is along the same line but in the opposite direction, and is the vector twice as long. So the eigenvalue here is negative 2. The vector is negative 1 1, and the eigenvector and the eigenvalue is negative 2. So by the picture we identify which vector is an eigenvector. So here we have another one. Oh, there, almost there. So 24, I guess is 25, isn't it? Yeah. But notice that this vector is just proportional to the first eigenvector we got over here, because it's minus 1 minus 1. So it's proportional. So we know that any vector proportional to an eigenvector is also an eigenvector. So, and you see the eigenvalue is still 4. So this is not new. We already have this eigenvector when we found it on the other side of the circle. And the same is going to happen for the negative, for this eigenvector here. Again, here we need to put one more, and there is perfect. So again, this vector is proportional to the other eigenvector, so it's nothing new, and the eigenvalue is still negative 2. And that's all we have. We have one eigenvector here, one there, and then the negatives, which don't matter. So by moving along the circle, we have found all eigenvalues and eigenvectors of the matrix, this matrix. If we go to the other side, nothing changes. We are just going around and around the circle. What happens if we increase the length? Nothing, because everything scales, so that is not going to do anything. And that's it. So this is how you use the geometrical interpretation of a matrix as a function to find its eigenvalues and eigenvectors. So now we are going to write the result that we found here on the paper. So from our computing program, we see that the geometrical analysis says that this matrix 1 3 3 1 has eigenpairs, given by V1. We said the first eigenvector was 1 1, and the corresponding eigenvalue was lambda 1 equal 4. And then it had another eigenvector, V2, that we identify as negative 1, 1, or any multiple of that, of course, with eigenvalue negative 2. So now that we know that, we can actually verify, so we can check. I'm going to check one, you can check the other. Check. Now that we have the picture clearly shows that these are eigenvalues and eigenvectors, but let's grab A acting on V1, that V1 over there, so we have 1 3 3 1, and we act on the vector 1 1. What happens? Well, we are going to have 4 4, which is obviously 4 times 1 1, which is lambda 1 times b1. So yeah, it's an eigenvector. You can do the other one. So exercise, do the other one. So that's how we can use the geometrical meaning of eigenvalues and eigenvectors to actually find them if we have a nice computer program to do it. Now let's try to find an analytical way to compute eigenvalues and eigenvectors of a matrix. And then when we do that, we need to go back to the remark we had before. Recall that what we need to do is we need to solve the eigenvalues eigenvector equations and and here v and lambda, these are the unknowns. These are the unknowns, and v has to be different from 0. And recall that this type of equations is different from the equations a acting on v equal a given vector, because here we have only one unknown, which is v. So the problem is that on our equation we have unknowns on the right hand side, not here. So what do we do? Well, we are going to try to separate the problem of here. What we need to do is we need to find both a vector and a number. We are going to try to separate that problem into two problems, finding the number and finding the vector. So how do we do that? So one way to do that is, let's move this term to the other side. Okay, so we have a acting on v minus lambda v equals 0. This is the 0 vector. Okay, recall that v is the same as the identity acting on v, because the identity matrix doesn't change the vector. So we can write down here a v minus lambda identity acting on the vector v. Now we have two matrices. This is a matrix with the same shape, equal the vector 0. Okay, so now we can pull common factor the vector v from here, and now we have a 2 by 2 matrix acting on the vector v equals 0, the vector 0. And recall that we are saying that we are looking for solutions where v is different from 0. Well, if we call, so here is an important breakthrough. This statement here says that this is equivalent to saying that that matrix we have over there, a minus lambda I, is not invertible. So let's see, why is that? So, well, we know something about invertible matrices. If a matrix B, for example, is invertible, so that means the inverse exists, then what happens? Suppose we have an equation of the form B acting on a vector equals 0. And suppose B is invertible, as we said. So B inverse exists. Okay, so we multiply by the inverse to solve the problem. Oops, this is not the B. B inverse acting on B, acting on the vector v, equal b inverse on the vector 0, and this is still the vector 0. And from here we get that this is equivalent, because what we get here is the identity matrix, and the identity acting on the vector is the vector. This is equivalent to say that the vector is 0. So the vector v equals 0 is the only solution of the problem when the matrix B is invertible, is the only solution. So if we say that we are looking for lambda such that this equation has non-zero solutions, then we are looking for lambda such that this matrix is not invertible. So in this problem, this is matrix B here. So this equation here, saying that this equation, we are looking for lambda such that this equation has non-zero solution, is equivalent to say that we are looking for lambda such that this matrix is not invertible. Because if it's invertible, then the only solution is 0. So what we need to do is we need to find lambda, so the eigenvalues, such that this matrix is not invertible. Notice that here we have V and lambda, V and lambda, V and lambda, but on this side of the if and only if of the equivalence, we have only lambda. There is no V. So this is a condition only on lambda, that this matrix has to be not invertible. This is what we gain. We get rid of V, the vector. We have only a condition of lambda. So now we need to find the condition on a matrix that determines whether the matrix is invertible or not. Well, this is what determinants are for. A determinant determines whether the matrix is invertible or not. And all that gives us the following statement. All the eigenvalues lambda of an n by n matrix A must be solutions of the following equation. Determinant of A minus lambda identity equals 0. Because this equation is equivalent to saying that this matrix is not invertible. This equation is going to give us all the eigenvalues. So once you have the eigenvalues, then given the eigenvalues, they are given by the solution of the part A of that equation, then the corresponding eigenvectors are solution of this equation, but now this equation is known. So now this is a simple equation of the form AB equal B, where, well, BB equal B, where this is actually 0, and this is known. This is a known matrix, so we can solve this equation and find the eigenvectors. One last comment, or a couple of comments. The determinant of this matrix A minus lambda identity, here recall lambda is a variable that we are looking for, and we are looking for by solution of this equation. This determinant is a polynomial function of lambda in lambda degree n. We are going to see that in a minute in the example. And this polynomial p of lambda, which is the determinant of A minus lambda identity, is called the characteristic polynomial of the matrix A. Okay, so let's see one example, and we are done for today. And then in the next video, we are gonna solve these equations for several matrices to have an idea of what are the different situations we can find for different matrices. But let's today solve one simple equation. So let's find the eigenvalues and eigenvectors, all eigenvalues, all eigenvectors of this matrix. Okay, so with our new found theorem here. So the matrix is 3, 2, 0, 3. Okay, 2 by 2. Solution. How do we do it? Well, we know from the problem that we need to decouple the problem of finding eigenvalues and eigenvectors, and we are first going to find eigenvalues. So one, eigenvalues only. Okay, what do we need to do? We need to solve the equation 0 equal the determinant of a matrix that is the original matrix A minus lambda, the identity matrix. And lambda here is the unknown, and this is an equation on lambda. Okay, so what equation is that? So we have the determinant of a matrix, and the matrix is matrix A, which is 3, 2, 0, 3, minus lambda multiplied by the identity matrix, which we know is 1, 0, 0, 1. So now we can do this multiplication and put lambda here. So let's do it, and we are going to get determinant. We still have matrix A here, we haven't touched it, 3, 2, 0, 3, and now we need to do minus lambda 0, 0, lambda. Now we have a difference of two matrices, so we do the difference, and we get that we need to compute the determinant of this matrix, and the matrix is 3 minus lambda, 2, 0, 3 minus lambda. Okay, but this is the determinant of a 2 by 2 matrix that has this form. So the determinant is always these two coefficients minus these two. So we end up with 3 minus lambda squared minus 0. So we end up with an equation which is lambda minus 3 squared. And that has to be equal 0. But you see, this is the characteristic polynomial. It's a polynomial of degree 2 because this is a matrix 2 by 2. This is what the remark we were saying here. Well, we have a polynomial, and we need to find the roots of that polynomial, but, well, this is very easy. I chose a simple example, and we have only one root, lambda 0, which is 3. So we have only one eigenvalue here, which is lambda 0 equal 3. Okay, and what do we do now? Well, let's go back to the theorem. This part of the theorem, we solve this equation and we obtain one eigenvalue, lambda 0. So now, with that eigenvalue, we put it here and we solve for b. This is the eigenvalue-eigenvector equation. So now, we go to the eigenvector part. So 2, eigenvector. And what do we need to do? We need to compute the matrix A minus lambda 0 identity, which is the matrix A minus 3 identity, because this is what lambda 0 is. And that matrix is matrix A, which is 3, 2, 0, 3, minus the identity matrix times 3. 1, 0, 0, 1. Well, but we did this calculation before, we can do it again. Well, a similar calculation, but let's do it one more time. This is minus 3, 0, 0, 3. So we are going to end up with a matrix which has a bunch of zeros, 0, 2, 0, 0. That is the matrix we need to work with. So now what we need to do is we need to solve the equation A minus 3 identity acting on a vector v equals 0. And we are going to write it in components. So we are going to use the vector v as v1, v2, and we need to find v1 and v2. Recall that this equation does not determine the magnitude of the vector, so we are not going to have both components. We are going to have one in terms of the other, so but not both, because if v is an eigenvector, AV is also an eigenvector. Recall that. Anyway, let's write down this equation explicitly, and this equation is 0, 2, 0, 0, acting on the vector with components v1 and v2 has to be the vector 0, 0. Well, from here we get only one equation, which is 2v2 has to be 0. The other equation is just 0 equals 0, so it doesn't matter. And the first equation says that the second component has to be 0. And what happened with the first? Nothing. We don't know. The first one is totally free. has to be non-zero. But other than that, free. So the vector we were talking about, the vector v, which is v1, v2, in order to be an eigenvector, has to be v1, 0. I can pull common factor v1, so a nice eigenvector is 1, 0 multiplied by v1. So I'm going to choose v1 to v1, and here we have lambda 0 equal 3, v0, let's call it v0, is the vector 1, 0. This is an eigenpair, eigenvalue, eigenvector of the matrix that we have in the problem. Let's check that this is actually correct. The nice things of computing eigenvalues and eigenvectors is we can always check. So we have 3, 2, 0, 3. We multiply by the vector 1, 0, and what do we get? Well, we get the vector 3, 0, which obviously is the vector 3, 1, 0. So yes, it checks out. So this is how you use the theorem to compute eigenvalues and eigenvectors of a matrix, and the idea is first you compute the eigenvalues. Once you have the eigenvalues, in this case it's only 1. In the previous case we had 2, recall. Now we have only 1, and we have the corresponding eigenvector, which is any vector proportional to the vector 1, 0. I chose one possible candidate, but 2, 0 or 7, 0 or -1, 0, or they are all possible eigenvectors. Let's finish this video with a graphical representation of the problem we just solved. Here we have the ground matrix, so we need to put the matrix that was 3 here. So let's put 3, oops, here, 3. We had a 3 also here, no, there. We have a 0 down here. There, oops, no, there. Oh, come on. So it's kind of hard. Let's see if we can do it like this a little bit better. There. And then matrix, the matrix has component 2. Okay. This is kind of annoying. There. That is the matrix we had. And now let's verify that this matrix has only one eigendirection. So we need to move. Oh, by the way, this is the eigendirection, the 1, 0. Okay. And then there are not eigenvectors. Notice that we are going to get this is the same eigenvector as before because it's multiple only. Okay, let's keep going. No, only one. This one here, that is the same, and there are no other eigenvectors. So only these two, nothing more. So that's all for this video. This is a good place to stop. See you guys in the next video.